All right, so I'm making this video to try and help you with the Tidewater Landing Stadium project, Part A. So if you're having trouble completing this, watch this video and hopefully that'll help you. And as a reminder, we're using the Oliver concert problem whenever we're working on the Tidewater Landing Stadium project because the Oliver concert problem has the same structure, right? It's the same, we're going to be using the same mathematical model to analyze the two different contexts. So let's start by reading through the Oliver's concert problem. That says, TJ's friend Oliver is planning on putting on a concert and he wants to sell tickets for the right price. He is confident that if he sells tickets for $5, then 300 Blackstone community members will come. For every $1 that he increases the ticket price, 6 fewer people will buy tickets for the concert. If it will cost him $4,200 to rent out the venue for the concert, what ticket prices should Oliver charge to make sure he is able to cover the cost of renting the venue? All right. So um, we have Oliver coming on a concert. We know if the tickets are $5, then 300 people will come. For every $1 he increases the ticket price, that the number of people who come goes down by 6 people and costs him $4,200 to rent out the event. So let's look at the table down here. What ticket price does Oliver need to charge in order to sell 300 tickets? Well, we see that right here. If he sells for $5, then 300 people come. So we're going to put $5. For every additional dollar that Oliver increases ticket price, how many fewer people come? See that right there. For every $1 he increases the ticket price, 6 fewer people come. So let's say 6. All right. And based on the information in the table above, how much can Oliver increase the ticket price before 0 people come to the concert? Well, remember, each time he increases the ticket price by $6 or by $1, 6 fewer people come. So how many times does he have to increase that price, right? How many dollars does he have to increase it by before all 300 of the people who were originally coming no longer are, and we're left with 0 people coming? Right? How many times does he have to increase the price before everyone who was originally interested in coming no longer is? We'll do that. We can figure out how many times does 6 go into 300, right? If every dollar that he increases reduces the number of people by 6, then he would need to increase the price. 300 over 6 is equal to 50 times or $50. Right? If he increased the price $50 or 50 times, then each of those would have 6 fewer people coming, resulting in all 300 people no longer coming, right? How many times does 6 go into 50 or go into 300? 50. Um, so if he increases the ticket price $50, then no one will come. If he was originally charging $5 and he increased it by $50, then the new ticket price, that's $55. All right, so we know he has to increase the ticket price by $50. It started at 5, so if he charges $55, then 0 people will come. Looking at the table down here, let X represent the ticket price that Oliver charges and T represent the number of tickets that he sells. Well, we know, so X, this is our ticket price. T, this is the number of tickets that he sells. So we're trying to create a table that tells us 2 different points, right? 2 different situations where we know the ticket price and the number of people who will come. We want to do that here too. So we see for T, if T is 300, means 300 people are coming. What needs to be true if 300 people are coming? Well, we know that the ticket price needs to be $5, right? That comes straight from our question. What does the ticket price need to be? Remember, X is ticket price for 0 people to come. Well, that's what we found in the last step, right? We know that if 55 people, or if the price is $55, then no one's going to come, right? He has to increase the price $50 to get rid of the 300 people. if he did that starting with an original price of 5, he's going to get up to 55. All right, now that we have these 2 points, we're going to use our formulas down here to create a linear equation that tells us for any ticket price, how many tickets can he sell? Right, for any ticket price X, how many tickets can he sell? And we're going to start with our slope down here. So if M is equal to T2 minus T1, then you want to look at our table. If we call this T2 and this T1, right? Just think about row 1, row 2, X and T. So T2 is here. That would be 0 minus T1, that's right there, minus 300 over X2, that's 55, minus X1. X1 is 5. If we do that, we're going to get negative 300 over 50. Negative 300 over 50, that's negative 6. Right, and that makes sense given the context we're looking at. If he increases X, the ticket price, by $1, then T should decrease by 6. We have negative 6 for our slope. Now we have to find our B. Right, we have our slope, now we need our y-intercept. To do that, we're going to take our equation T is equal to negative 6x plus B. We want to evaluate it for one of these 2 points up here, right? One of these 2. I'm going to choose this one just because it's nice to work with 0, but if you choose the top point, you will get the same answer. So in this row, we have T is equal to 0, and we have 0 is equal to negative 6 times X, where X is 55, plus B. If we multiply those two out, we're going to get 0 is equal to negative 330 plus B. Adding 330 to both sides, we're going to get 330 is equal to B. And that means that our total demand equation, right, again, in the form T equals mx plus B, and this mirrors the y equals mx plus b form that you should be familiar with. All we're doing is replacing the y with the t. All right, so think about this as y equals mx plus b, that's a linear equation, but we're plugging in our values for x and t to get a linear equation in the form t equals mx plus b. So m is negative 6, t is equal to 330. And so our final demand equation would be t is equal to negative 6x plus 330. Right? This is our demand equation. Okay, so how is that going to help you with your project? Well, if we go over here and see that it looks very similar. We have a lot of the similar stuff going on. So we're trying to create a demand function that's going to tell us for any ticket price, how many people are going to come to Tidewater Landing Stadium, right? So the variables are the exact same. But to do this, we're going to use different values. So you're going to come up with these values. The first thing I want you to think about is look at row A and think, what is the highest ticket price that would still allow Rhode Island FC to sell tickets to all 10,500 seats in the stadium? So Tidewater Landing Stadium has this many seats, 10,500. And let's say Rhode Island FC wanted to sell out, wanted to sell every single one of them. They want to make as much money as possible. So what do you think is the highest price that they could charge and still have enough people interested to fill the stadium, to sell out all of the seats? So I want you to think about using your understanding of the local economy, of the people around here, right? You know the community. What do you think that value is? Is it $5? Is it $10? $100? $1,000? How much money are people willing to pay? So what's the highest price that would still get 10,500 people in the stadium? Then I want you to think about if that price started to increase, right? For every dollar that that price increases from whatever you chose here, that's what you're going to put here. So whatever number that is, use your best judgment, kind of, you know, use what you know about the people around here. As the price goes up, how much are they going to be willing to continue to buy tickets to the stadium? And then if we move down here, based on your answer, table 1, how many dollars does the ticket price need to increase before 0 people buy tickets to the game? Remember, that's very similar to what we have going on over here. We're saying we have some amount of, right, some ticket price that corresponds to some amount of attendance, and then we're increasing that ticket price to decrease that attendance. And so how many times do you have to increase the ticket price to and lose this many number of people before all 10,500 people no longer are attending? And then after that, you want to do the same math that we did for the Oliver concert problem, right? Identical process to what we did here, but with your values. And think about what ticket price had 10,500, what ticket price meant that no people were coming, and what is the t equals mx plus b formula that looks like that. And really, really importantly, make sure you're looking to the next page and you're writing that formula here. And make sure you're completing all of these questions too that are interpreting this equation in the context of the problem. If you do all that, then you'll be good for part